Hey everyone, welcome back to Tyler Maxwell's Chemistry. Hope you guys are having a good day. Today we're going to be talking about quantum numbers, which is still more of Chapter 7. But we're going to go over what the quantum numbers are and what they're basically representing. And quantum numbers are used to define electrons. So quantum numbers specify where an electron is in space, and basically no electron has all four of the same quantum numbers. So they're used to specify where electrons are, how much energy electrons have, and so on and so forth. So we have the four quantum numbers here. They're NL, ML, and MS. Okay, so our first quantum number, N, is our shell, which is basically our energy level. So this is sort of the broadest term you can think of, but this is called the principal quantum number. So it's the principal energy level of the electron. L, or the angular momentum quantum number, is used to specify the subshell. So it's sort of more specific than the shell, but it's used to specify sort of an area in space within the shell where the electron is. Our ML is the magnetic quantum number, and it's used to specify the orbital. So again, a further in-depth or further specific idea of where the electron is. And then spin is the spin quantum number. So it's a little bit less interesting. It's just spin up or spin down. So electrons have two spins. They could be plus 1/2 or minus 1/2. So spin has to be either plus or minus 1/2. So that's why no two electrons can have the same quantum number, because if you have two electrons in the same orbital, you'll have one electron that's spin plus 1/2 and one electron that's spin minus 1/2. So they can never have the same quantum number. So first off is the shell, or principal quantum number. So this one tells you basically the energy level of the electron. And you can sort of look at the periodic table I've got here, which will help identify that. So remember, your shells or energy levels sort of correspond to the periods on the periodic table, where you have energy level 1, 2, 3, 4, and 5 is the periods on the periodic table. Okay, so starting off with that, the subshell, L, is used to specify whether the electron is in the subshell S, P, D, or F. So these are basically regions in space within the shell where the electron is located. So the S is sort of spherical, so it's sort of like a sphere. This is our S. Our P is sort of like a dumbbell shape, so if this is the nucleus, these are both the nucleus. So the P is sort of like that. So it's basically just a region in space where the electron can be located. So an S is sort of like a spherical region around the nucleus. The P is sort of a dumbbell-shaped region around the nucleus, but it's just an area where we could find the electron. Okay, so L specifies subshells, which are basically these sort of shapes, and they could be S, P, D, or F if L is 0, 1, 2, or 3. Okay, but remember, not every energy level has all of the subshells. Some energy levels only have S, some only have S and P. So this is why our L is basically, L has to be equal to N minus 1. This is the general rule, where N is our principal energy level. So these are the values that L can be. So as we increase an energy level, we have more subshells available to us. So if energy level is 1, so we have 1 minus 1 is 0. So at energy level 1, we can only have the S subshell, and that's true because if we look at the first energy level, see there's only two elements there, so they only have the S subshell. That's why L has to be equal to 0 if n is equal to 1. If n is equal to 2, we have 2 minus 1, so that's equal to 1, so L can be 1 or L can be 0. So that means S and P. So if we come here and look at the periodic table, so we have our S and we have P electrons. Okay. So if our first one for D is n is equal to 3, so 3 minus 1 is 2. So at energy level 3 we can have S, P, and D subshells, or electrons in those subshells. And if our n is equal to 4, then we can have F electrons too. But that's the general rule. N minus 1 is the possible subshells that you can have for an electron of that energy level. And for our next one is ML. So this is orbitals. Basically, the S subshell has 1 orbital, the P subshell has 3, D subshell has 5, and the F has 7. Okay. And each orbital, as we know, can hold 2 electrons. One with a spin up, plus 1/2, and one with a spin down, minus 1/2. You see this as like plus or up 1 arrow, down 1 arrow. So basically, each one of these orbitals corresponds to a value of ML. So ML can be plus or minus L. So let me get rid of MS for a second. So ML is equal to plus or minus L. So if our L, say our L is 0, so it's an S orbital, well, ML has to be equal to 0. So if we look at our S, see there's only one orbital in the S, and that's an ML of 0. If we look at our P, so for our P, L is 1, remember 0, 1, 2, 3. So for our P, L is 1. So ML can be plus or minus 1, which means that it could be minus 1, 0, or 1. And as you can see there, 3 orbitals. So if we look at our P here, negative 1, 0, positive 1. See, we have three separate orbitals for the P. So this trend, ML of, or an L of 2, D has 5, negative 2, 1, 0, 1, 2. That's 5 different orbitals. So this is our ML, or our orbitals. So remember, our S has 1 orbital, P has 3, D has 5, F has 7. If there's 2 electrons per orbital, it's 2 electrons in the S, 6 in the P, 10 in the D, and then 14 in the F. And this is also, you can see sort of on the periodic table, 2 electrons in S, then we have 2 in P is 6, see, 3, 6. This is our D's here, remember our D block there, so this is a total of 10, right, 10 electrons in the D, and then our F here, right, is 14, right, so just think about it like that. 2 for the S, this is our P, so that's 6, D is 10, and F is 14, so divide by 2 is 1, 3, 5, and 7. And that corresponds to the total values that ML could be. Alright, well, I hope you guys enjoyed this video. Give me a like, thumbs up, comment, subscribe. Let me know what you guys want to see, what other videos, what topics you guys want to see me cover. So I hope you guys have a good day. Alright, Tyler Maxwell signing out.